Okay, this set of notes is on calculating means and standard deviations of discrete distributions. And it relates to probability, but also ties very closely to finding the mean, the measures of center and spread for discrete distributions. And we need that to help describe data. And also ties, we're going to use this information for when we transform and combine random variables. So we had been calculating the mean by adding up all the x's, and this means adding up all the values and dividing by the sample size. And we said the standard deviation, the variance, this is the variance symbol, was every individual x minus mean, taking that difference and squaring it. So basically squaring all the differences from the mean and then taking an average. And the standard deviation is just a square root of that. Normally today we talk in standard deviations because it's easy for us to take square roots. Initially they talked about variance only because it was difficult to take a square root with a calculator. It's a piece of cake. So what if instead of having a list of data, we knew how often certain results occurred, either because we knew it by simulation or by experience? For instance, we know that when we roll a dice, the chance of getting a 1 is 1/6, and a 2 is 1/6, and a 3 is 1/6, et cetera, et cetera. So how can we calculate the mean and standard deviation based on doing that? Well, first we need to know what all the possible outcomes are. Well, rolling a dice, the only possibilities are 1, 2, 3, 4, 5, and 6. And in this case, the probability of getting any one of those is 1/6. And so here it is represented in the table. These are what our possible outcomes, the 1, 2, 3, 4, 5, and 6. So these are our dice outcomes. And these are our associated probabilities, the 1/6 for each one of them. Now this happens to make a valid probability distribution. I need to talk briefly about that before we get into our computations. To be a valid probability distribution, our probabilities must sum to 1. And if I added all these up, they actually do sum to 1, so that's good. And then the next thing is the probabilities must lie between 0 and 1 inclusive. In other words, you can have a probability of 0, it might never happen. You can have a probability of 100%, which is what's guaranteed to happen. But there's no such thing as a negative probability, and there's no such thing as a probability greater than 1. In other words, when we sum everything up, we can't have any negatives, we can't have any positives, and it has to sum to 1 whole. So does a table represent a valid probability distribution? Well, we already said that it summed to 1, because we have 6 of these, 1/6 plus 1/6, et cetera, all the way to summing to 1. And none of the probabilities are negative and none of the probabilities are greater than 1. So yes, it represents a valid probability distribution. So we have this formula, and this is the formula for calculating the mean or the expected value. Now I want to talk to you just a little bit about the mean and the expected value. Why are they the same thing? Well, consider this. If we knew that the class average on a test was at 87, and I randomly drew a name from the hat, and you didn't know who it was or anything about that person, and I asked you to guess what they made on the test, well, your best guess would have been the average, would have been the 87. So you would have expected that random person that you knew nothing about would have made an 87 because that was the average of the class. So that's what this means. The expected value is on average what we expect to happen. What we expect to happen is the mean. Now, this is the formula for calculating the mean of a discrete probability distribution. So here's your formula, and you're going to need to be able to write that down. Now it is on the formula chart. So we have our individual x's and the probability of them occurring. So this one represents an x, this represents an x, this represents an x, this represents an x, this represents an x, and this represents an x. And their associated probabilities happen to be all the same, which are 1/6. So when I multiply 1/6 times 1, and then add it to 1/6 times 2, plus 1/6 times 3, and I add all those up, I end up getting an expected value of 3.5, or I could say my mean was 3.5. Now, what's kind of interesting about that is when I roll a dice, I can't get a 3.5. However, this is what on average I would expect to happen. And that's like saying we made an 87 was the test average, but the only grades you could make were multiples of 5. So in other words, you could make it an 80 or an 85 or a 90 or 95, but you couldn't have made an 87, but the average score happened to be 87. So this is what this is saying. The average score, the expected score, we'd expect to be 3.5. When we get to variance, variance, of course, is the individual value minus the mean. Well, our individual x is for x of 1, x of 2, x of 3, x of 4. We had an x of 5 and an x of 6. And here's our expected value, or a 3.5. So the individual x squared times the associated probability. The individual x minus the mean squared times its associated probability. The individual x minus the mean squared times the associated probability. And when we sum that up, we can go through all the calculations and we get 1.7, we end up getting 2.917 as our variance. And remember, the variance is just the standard deviation squared. Now, if I take the square root of that, I get the standard deviation. Now, this will be showing your work. On the calculator, it's very nice. So I've already input my data, and I happen to input it into column L2 and L3. So I have my dice rolls, which could have been a 1, 2, 3, 4, 5, or 6. And this just represents 1, 6. All I did, just so you know, is I took 1 and divided by 6, press enter, and it got that. So I'm going to go stat calc, one variable statistics. And my X list is an L2, so second 2. My frequency is an L3, so second 3. All right. And then I'm going to go press enter, and it gives me my information. There's my mean of 3.5, and here's my standard deviation of the population of 1.707. Now, it does not give you the variance, so to get that, I'm going to have to square the 1.707. If I square it, I'm going to get about 2.917. If I scroll farther down, I find my minimum value that I could have gotten was a 6. My median was 3.5. My maximum value was a 6. It also gives me my Q1 and Q3. All right, so let's take a look at putting this into action with some other problems. So a commuter must pass through 5 lights on her way to work. She estimates the probability model for the following of lights she hits is shown below. Calculate the expected value mean and the standard deviation of variance showing all your work. Well, the very first thing I'm going to do is I'm just going to go very quickly and enter that information into the calculator. And so I'm going to press in 0. Now we go from 0 to 5, so 0, 0, enter, 1, enter, 2, enter, 3, enter, 4, enter, 5, enter. Then the next thing is 0.1, enter, 0.25, enter, 0.30, enter, 0.2, enter, 0.1, enter, and 0.05, enter. All right, so I'm going to go ahead and run this without showing my work. I'm going to go stat calc, one variable statistic. My list is an L2 and L3. Once again, second 2, second 3. And I end up getting 2.1 and a standard deviation of 1.3. To get to this, I had to take the 1.3 squared, and that equals 1.69, because the calculator doesn't get variance. So the question is, does this represent a valid probability distribution? Well, when I add these up, go ahead and add all these values up, they happen to equal 1.0. Because they equal 1.0, that's a good thing. And then I need to check all of them are positive and none of them are greater than 1. So I can't have any negatives, and they sum to 1. That's a valid probability distribution. So I need to be able to show my work. So calculating by hand, 0 times 0.1. So 0 times this, plus 1 times this, plus 2 times this, plus 3 times this, plus 4 times this, plus 5 times this, equals 2.1. And so on average, we can expect to have to stop at 2.1 of the 5 red lights. On average, we expect to stop at 2.1. Calculating the variance, it's our x value, which our first x value, 0, minus our expected value of 2.1. Let me go ahead and circle that. So this is our expected value. And so we're going to plug it in every single time, squared times the associated probability, and we do that all the way across. So our x value minus our mean squared times the associated probability. Our x value minus our mean squared times the associated probability, all the way till we get the last one, and we end up getting 1.69. The next one says complete the probability distribution and calculate the expected value. Well, there's kind of a problem here because the very first thing is I add these up. I go, okay, is this a valid probability distribution? And I go, and I take 0.15 plus the 0.3 plus the 0.35, and it doesn't equal 1 whole. But if I take 1 minus that value, I end up getting 0.2. So this missing value right here needs to be 0.20. And now if I add those values up, I get a valid probability distribution. All right. So what do I need to do to put this in the calculator? So let's do this in the calculator first. So stat, edit. I'm going to clear these out. Clear out. And I end up with my x values this time of being 2 enter, 4 enter, 6 enter, 8 enter, and my probabilities of 0.15, 0.3, 0.35, and 0.20. So stat calc, one variable statistics, happens to be an L2 and L3, so second 2, second 3. And I end up getting an expected value of 5.2 and a standard deviation of 1.39. Once again, to square, I'm going to have to square this. I'm going to have to square the 1.39 in order to get this value right here. All right, so that's going to have to be squared. Now to show my work, because I didn't do it on this one, the expected value is the sum of the x's times the associated probabilities. So in this case, it's going to be 2 times 0.15 plus 4 times 0.3 plus 6 times 0.35 plus 8 times 0.20. Now, to abbreviate our work, we can just go 2 times 0.15 plus plus 8 times 0.20. All right, so that's our expected value. Our variance is just going to be the sum of the individual x's minus the mean, that squared times the associated probabilities. All right. Well, we just calculated our expected value, and we said that that was 5.2. So in this case, it's going to be 2 minus 5.2 squared times the associated probability of 0.15 plus 4 minus 5.2 squared times the 0.3, which is the associated probability, plus 6 minus 5.2 squared times the associated probability plus 8 minus 5.2 squared times the probability of 0.2. And once again, we can abbreviate that. We can abbreviate it by just showing the first one and last one. So we can just go 2 minus 5.2 squared times 0.15 plus plus 8 minus 5.2 squared times 0.20. And that, in that case, equaled 3.76. To take the standard deviation, I just take that whole thing and put it under the radical. So I take the square root of 3.76. Okay? All right, so the next problem, problem 3, is a little more challenging. All right? So an insurance company charges $1,600 annual for car insurance. The policy specifies that the company will pay $3,000 for a minor accident and $10,000 for a major accident. The probability of a motor having a minor accident is 0.22, and the probability of a major is 0.03. Complete the probability table below for how much money the insurance company will make a single policy. Well, let's talk about this. All right, so if you don't have an accident, they take in $1,600, so they actually make $1,600. However, if you have a minor accident, they have to pay out $3,000. So they're taking in $1,600, but they're subtracting $3,000. And if you happen to have a major accident, they're taking in $1,600, but they're paying out $10,000. So in this case, if you don't have an accident, they make $1,600. If you have a minor accident, they're going to lose, and they're going to lose $1,400. That's a negative $1,400. And if you have a major accident, they're going to lose $8,400. Now, they told us the probability of this type of a minor accident is 0.22. The probability of a major accident is 0.03. So the probability of not having an accident is going to be 1 minus that, which is 0.75, because this has to add up to one whole to make a valid probability distribution. Well, now that I have that, I can go to Stat Edit, and I'm going to press in how much money I make. Well, 1,600. I could lose 1,400, or I could lose 8,400. The probability that I make 1,600 is 0.75. The probability that I lose 1,400 is 22%. The probability that I lose, that you have a major accident, and I lose 8,400 is 0.03. So stat calc one variable statistic L2, L3, and we find out that on average we expect to make $640, and we have a standard deviation of $2,014.55. If I square that, I get this huge number. All right. These are swapped. This should have been the variance. Okay, those happen to be swapped. All right. So our standard deviation is 2014.55, and our variance is this. And if I were to actually show all my work, here's what I would have to do. The expected value in this case is going to be 1,600 times 0.75 plus a negative 1,400 times 0.22 plus a negative 8,400 times 0.03. And as we said before, that equals 640 bucks. The variance is going to be the $1,600 minus the mean, 640, that squared times 0.75, plus a negative 1,400 minus 640 squared times 0.22, plus a negative 8,400 minus 640 squared times 0.03. And that's going to equal approximately 4,058,000, and that's within rounding. And then if I take the square root of that, I get the standard deviation. All right, so that concludes that video.